In this video, I'm going to work out the same problem we just worked out, namely that of computing the convolution of x of n given by alpha to the n u of n with h of n given by beta to the n u of n. But what I'm going to do differently from what I did in the last video is that I'm going to not draw these signals, or I'm not going to use the help of pictures in order to perform this convolution. I think one of the important things that you should develop from this class is the skill to be able to manipulate these convolutions just from the mathematical formula, as well as get some intuition on how to perform this convolution by looking at pictures or looking at drawing these signals. Okay, so I will now try to work the same problem and see that we can get the same solution without actually drawing these signals. Okay, so what we need to evaluate is this summation here given by summation over all values of k, x of k times h of n minus k. Okay, so we'll begin by first looking at x of k, which is alpha to the k u of k, and h of n minus k. So how do I get h of n minus k? Well, I can simply plug in n minus k wherever there is a n in the expression for h of n, or I could first write it as h of k and then plug in n minus k wherever there is k in the expression. So h of n minus k is given by beta to the n minus k times u of n minus k. Okay, so what I really want to evaluate now is to evaluate the sum over all k of alpha to the k times beta to the n minus k times u of k. Maybe I'll write it in two steps. Alpha to the k u of k times beta to the n minus k u of n minus k. Okay, this we can rewrite as k going from minus infinity to plus infinity, alpha to the k beta to the n minus k times u of k times u of n minus k. So how do we evaluate this summation? Well, if I look at what's going on here, this seems like this is a term that is actually easy to sum, because this looks like I could write this as alpha over beta raised to k times beta to the n, and I can pull the beta to the n outside of the summation. But this term requires a little more thought as to how to handle this. What is u of k times u of n minus k? So remember, u is the unit step function, which is defined as follows. So u of k is 1 for all values of k that are greater than 0, and it's 0 if k is less than 0. Similarly, u of n minus k is a function which takes the value 1 if n minus k is greater than or equal to 0, and it takes the value 0 if n minus k is less than 0. So if you think about what's happening here, each one of these functions actually takes either the value 1 or takes the value 0 depending on n and k. Okay, but what we are going to do is to figure out when this function is non-zero. So for a fixed value of n, what will be the range of values of k for which this function is non-zero? Well, it looks like what we need to satisfy is the following, right? K needs to be greater than 0 for sure. That I get from the fact that I need u of k to be 1. But it also looks like we need n minus k to be greater than 0, which means we want n to be bigger than k. So actually I will write it like this. We want 0 to be less than or equal to k. I get that from here. And from here, we get the expression that k needs to be less than or equal to n. So only for these values of k is the function u of k times u of n minus k non-zero and is given by 1. Otherwise, this is 0. For all other values of k, so that helps a lot, because what this tells us is that I could take the summation given here. We'll begin with the summation for y of n, which is alpha raised to k, beta raised to n minus k, u of k, u of n minus k, for k between minus infinity and plus infinity. And it says, okay, unless k is between 0 and n, the summation, this term is going to be 0. So what that first of all means right away is that if n is less than 0, then clearly there is no value of k for which u of k times u of n minus k is non-zero, because we really need k to be between 0 and n. If n is negative, we need k to be bigger than 0 and smaller than n. So if n is negative, there are no such values of k which satisfy this. So this gives us the result that if n is less than 0, y of n is 0. If n is greater than or equal to 0, then y of n can be written as summation from 0 to n, alpha to the k, beta to the n minus k times 1, which is beta to the n times k equal to 0 to n, alpha over beta raised to k, which is beta to the n times 1 minus alpha over beta raised to n plus 1 divided by 1 minus alpha over beta, which we can simplify to beta to the n plus 1 minus alpha to the n plus 1 divided by beta minus alpha. So this is the final result. The final result is that if n is less than 0, then y is 0. If n is greater than 0, then y is given by this nice expression here. Now notice that we could have succinctly written this as this. We could have combined this result, and we could have written it as something multiplied by u of n. So this is the final result. Hopefully this coincides with the result we obtained. There you go. So this is what we obtained when we did this convolution pictorially. And you can see it's exactly the same thing as here. It looks like I wasn't careful when I did it the last time. I should have had a less than, greater than, or equal to 0 here. Yeah.